All right, guys, so the concept I want to go over with this video is a little bit of biomechanics, it's a little bit of functional anatomy, it's also a little bit of some of the anatomy that we're going over currently in class. One concept that I really want you to understand is this relationship between force, mass, and acceleration, right? So what we see up here on the board, this is Newton's second law. Newton's second law states that force equals mass times acceleration. So what, right? What I want you to understand is I want you to understand the relationship between force, mass, and acceleration. Why do we need to know this? Well, because we're going to have patients in our clinic and we're going to have to figure out why they can't lift themselves, why they can't get out of a chair, why they can't lift a cup, plate, another device up to an overhead shelf. And a lot of it directly relates into force equals mass times acceleration. Now, what I want you to think about is I don't just want you to think about the equation and memorize the equation, but like I said earlier, I want you to think about what it means. My mass is directly related to my force. My acceleration is directly related to my force. So what that means is that the mass, when it goes up, my force also must go up. When my acceleration goes up, my force also must go up. That's literally what it means. So I'm going to erase this really fast. I'm going to rewrite it because we're going to start talking about what this equal sign means, okay? So here's what we're going to do. We're going to review force equals mass times acceleration. Force equals mass times acceleration. Nice and easy. Now, the point I want to bring up is I want to bring up what equals means, okay? So what equals means is that everything on this side of the equation and everything on this side of the equation are in balance. And that's a very important concept to understand. Okay, again, this is not just a math problem. This is literally a lot of what we're going to do as physical therapists. So when my left side of the equation and my right side of the equation are in balance, what I want you to start thinking about is that this equal sign is really going to mean isometric, okay? And we can kind of figure that out, right? So when I'm holding my arm out away from my body, the forces are still acting on my arm. Mass, my arm has mass. I have acceleration. In this case, gravity is going to provide my acceleration. My acceleration is moving downward. What is making my arm stay in this position are my muscle contractions, right? So really and truly, what we have here is we have a balance of forces, okay? And the way I like to explain this is I have a balance of up and down force, right? So if I have an equal sign here, force equals mass times acceleration, what this means is that my downs, because mass is going to pull me down, gravity or acceleration is going to pull me down. My force needs to equal those in order to make a stable structure or a stable unit or a stable system, right? If I have an equal sign here, that means that this is stable. And in fact, I'm going to draw these arrows pointing up because my force is going to be going upward, okay? So that was a mistake I made, but my arrows going up, my force should equal my arrows going down, okay? So think about the person that's right here in the little picture, okay? I'm the person moving now from position 1 up to position 2. Now we have a whole different scenario here because now the forces are not equal. And in fact, what I want you to think about is if force, the same basic equation here, if force is greater than mass times acceleration, I'm going to have a concentric contraction. And that makes a lot of sense. right? Because I still have my mass that's pulling downward. I still have my acceleration pulling downward. But now I have more force. I have more F's, right? And so my force is greater than my mass or acceleration, which means I'm moving upward. In an eccentric contraction, same concept, we just flip the sign, right? Because now my force is less than mass and acceleration. Okay? Again, same thing happens. My mass is moving downward, my acceleration is moving downward. But I only have one F moving down, right? I have less F, which means that I have motion that my net force, my net motion, is moving in that mass times acceleration sign. So I'm moving downward, but force is playing a little bit of a role, so I'm not moving as fast. Okay, that's basically what that means. The other concept that I want to kind of get into is this concept of joint angle. Okay, so with joint angle, our joint angles are going to play a key role in how much force is produced as well, right? And we kind of know this. We know that I can hold a weight out, let's say this red pen's my big weight. I can hold a weight out at about 30 degrees of shoulder flexion, and it's not going to be as difficult as when I hold that weight out at 90 degrees of shoulder flexion, okay? And there's a couple of reasons why. Number one reason is going to be joint angle. So what we're going to do here in this little picture is we're going to call this little joint theta, right? Because that's what they do in geometry. So this little joint's going to be called theta. Now what we're going to see is that if we think about our motions moving on a little bit of an axis, okay, or a graph, my y direction is going to be my vertical direction, my x direction is going to be my horizontal direction, okay? So in terms of how this plays into joint angle, if my acceleration is gravity, okay, and we're going to mean that gravity is going to move in the y direction or the vertical direction, what we're going to do is we're going to add on sine of theta, okay? I'm going to take it way, way back to geometry, okay? Remember, sine, cosine, and tangent. Okay, so sine is going to be my y direction, cosine is going to be my x direction, and we're not going to worry about tangent for right now. But when I'm dealing with gravity, what I need to understand is that this joint angle is going to directly relate to mass and acceleration, okay, especially mass. So that my sine of theta will directly affect mass and acceleration, therefore directing force. Okay, so the larger that joint angle is, the more force I'm going to have to provide.